So it's a pleasure to introduce the next speaker, Butler.
So what I'd like to talk about is a result which tells us that the existence of a completely integrable convex Hamiltonian on the cotangent bundle of a compact manifold is an invariant of the smooth structure of that manifold. A non-trivial invariant, in fact. So just to briefly go over the outline of the talk, I just want to remind you at the outset of the psychological setting for Hamiltonian mechanics and the famous Liouville-Arnold theorem that characterizes locally what a completely integrable system looks like. And then to state a motivating question and sketch some results about the topology of configuration spaces of completely integrable convex Hamiltonian systems in low degrees of freedom. And then this motivating counterexample of Bolsunov and Taimanov will give me an opportunity to formulate a definition of what a topologically tame completely integrable system is. And then sketch some further results in three degrees of freedom, showing the link between the geometrizability of a three manifold and complete integrability. And then finally, I'll finish with this result that shows that not only are there topological obstructions to the existence of such completely integrable systems, but there are even smooth obstructions. Okay. So just to psychologically locate ourselves, I'll be dealing with mechanical systems that arise from a variational principle. And of course, we know that the solutions, the stationary curves to this variational principle satisfy the Euler-Lagrange equations, and more conveniently, allowing us to introduce some geometry of the cotangent bundle, they satisfy Hamilton's equations. Okay, and so we can set our mechanics on the cotangent bundle by introducing the canonical Poisson bracket, and the solutions to Hamilton's equations, the variation that are characterized by this variational principle satisfy these very nice equations. And the phase space of our system then is the entire cotangent bundle of M, and I think of M as the configuration space of our mechanical system. Okay. Now, just a little bit of terminology. We'll say that f and h, these two functions, these Hamiltonians, Poisson commute if their Poisson bracket is identically equal to 0. And so what that tells us then is that the flow of the Hamiltonian f is tangent to all the level surfaces of h, and in addition, the Hamiltonian flow of h commutes with that of f. So the existence of Poisson commuting functions gives us two things for the price of one, invariant surfaces and symmetries. And the theorem of Liouville from the 19th century characterizes locally the situation in the regular case. So suppose that we have n independent Poisson commuting functions on our cotangent bundle, and suppose that we have a regular common level set that's compact of these n functions. So then we know that this regular level set is an n-dimensional torus. We know that, in fact, there's an open neighborhood that's diffeomorphic to this toroidal cylinder, Tn times Rn, and that this neighborhood admits action angle coordinates in which all of the Poisson commuting functions are functions only of the actions, the I variables, and the flow linearizes on the individual tori given by the theta variables, holding the I variables fixed. Okay, so in some sense, what the Liouville-Arnold theorem tells us is that integrable systems are all the same, at least on the regular levels. And of course, as we are all aware, that means that the singular levels contain all of the important information about the configuration space M. So if you look at common examples of integrable systems, my favorite example being the total lattice, you see a theme that runs through these examples, and that is that the configuration space is relatively uncomplicated in a topological sense. So, for example, we know of no examples of completely integrable mechanical systems on the cotangent bundle of a hyperbolic manifold. And also what we see from the typical examples, the dynamics are typically uncomplicated. Obviously, in the regular levels, we know that the dynamics of the completely integrable Hamiltonian system are uncomplicated because they're simply translation flows on Tori. Okay, so these are sort of two guiding questions that have informed research in this area. So to make things a little bit more precise, we will take M as a closed n-dimensional smooth manifold. It's our configuration space for the mechanical system in question. And we'll say that our Hamiltonian is convex if fiber-wise it's a convex function on the cotangent bundle. So there's the more precise question. The question is which manifolds can be the configuration space of such an integrable convex Hamiltonian. So I am thinking of mainly mechanical systems, that is, mechanical systems being of the form kinetic plus potential, but in general the convexity is the only requirement really that we need for these theorems. Okay, so here are some results in 2 and 3 degrees of freedom. So just to remind you of the uniformization theorem for surfaces, each surface admits one of 3 geometries, either flat Euclidean geometry, hyperbolic geometry, or spherical geometry. Okay, and a theorem due to Kozlov, which was proven in '79, is that if we have a convex Hamiltonian H on a compact surface, and it's real analytically integrable, so in this case it needs only one additional independent analytic integral, then M admits exactly one of the 2 geometries, either flat or spherical geometry, and in particular there are no hyperbolic geometries allowed. Right? So this tells us that the existence of an analytic integral, an analytically integrable convex Hamiltonian on a surface is quite a restrictive property. And then shortly thereafter, Fomenko with a number of collaborators created a theory of integrable 2 degree of freedom Hamiltonian system with an assumption on the integrals. So I said at the outset that we need some sort of notion of what it means to be topologically tame in addition to being completely integrable. And in this case, the notion that was struck upon is that either we have analytic integrals or else the extra integral is a more spot function. So that's in 2 degrees of freedom. And then Fomenko was able to show that the regular levels of this Hamiltonian are graph manifolds. So relatively uncomplicated 3-dimensional manifolds. And then Gabriel Paternane proved in the non-degenerate case, Moser in the analytic case, that in addition, the dynamics, not only is the topology of this 4-manifold relatively uncomplicated, but the dynamics are also uncomplicated. The topological entropy must vanish. Okay. Iskander Taimanov, in his PhD dissertation, studied the problems in higher dimensions. And I should say that there is it is a very difficult question how to correctly generalize the classification theorem of Taimanov's to higher dimensions. although our next speaker, Zung, will talk about, well, he won't talk about it, but he's done work on this problem. So Taimanov's result it was stated for geodesic flows, but as I said, it obtains for convex real analytic Hamiltonians. So suppose we have a real analytically integrable convex Hamiltonian on the cotangent bundle of this closed manifold M. Then there are a series of consequences. First, the dimension of the first homology group is at most the dimension of the configuration space. The second is that the manifold M itself is finitely covered by has a finite covering by a manifold with an abelian fundamental group. And the third is this injection on the level of cohomology rings from the B1 dimensional torus's cohomology ring into the cohomology ring of M itself. So these are quite strong restrictions, and the implications, the implications of this theorem, for example, this gives us another way of demonstrating Kozlov's theorem in 2 degrees of freedom, and then in 3 degrees of freedom, it implies that up to homotopy, M has to be a sphere, a product of spheres, or well, a torus, which is a product of spheres. So again, relatively uncomplicated configuration spaces. And then Gabriel Paternain proved that the existence of a completely integrable Hamiltonian system with non-degenerate first integrals implies the vanishing of topological entropy. So we have these sequence of results which tell us that analytic integrability or non-degenerate integrability, which is slightly stronger than analytic integrability, that these imply both topological and dynamical simplicity of our integrable system. And as I mentioned, Wenzhong has developed a theory of how to characterize the integrable systems with non-degenerate singularities. And I'll just say that it's a relatively involved theory. Okay, so it came as a bit of a surprise, I think, that that an integrable system could have a positive topological entropy, so be dynamically complicated. And this example of Bolsanov and Taimanov's is quite informative. So they gave us an example on the mapping torus of a two-dimensional so for concreteness, they gave us an example on the mapping torus of this two-dimensional toral automorphism. And they showed that there's a natural Riemannian metric whose geodesic flow is completely integrable. And the suspension flow of this automorphism is embedded in the singular set. And so this is where the positive topological entropy is generated. And this, all in all, I think is quite surprising. The integrals of this come about in the following way. In appropriate coordinates, the Riemannian metric can be written as the following diagonal quadratic form. This is on the universal cover in the appropriate diagonalizing coordinates for this linear map A. And what's striking is that both y1 and y2 are cyclic coordinates. So the corresponding momenta functions are integrals in involution. They're not invariant, though, under the action of the fundamental group, but they do a little bit of work, and they can show that they can construct functions which are invariant and descend to the cotangent bundle of the mapping torus. So one function which is which is independent, in addition to the Hamiltonian of this, a function that's independent and in involution is the product of the two momenta functions. That follows from the fact that the determinant of A is 1. And then there's this additional queer integral, which is, well, actually Taimanov's theorem tells us that it has to be smooth, but it cannot be real analytic. And it's constructed from these momentum functions in a clever way. Now, this example, striking as it is actually, it actually fits into the theory of total lattices, which we heard about earlier in the week. And it's associated to the simplest total lattice, the one-dimensional A11 lattice, and it generalizes to higher dimensions. So this is not an isolated example, but actually is something that's quite interesting and occurs often in nature, as it were. So before I move on, I should say that this mapping torus here, the configuration space, is an example of Sol geometry. So this is quite a natural example to think about also. Now, let me tell you a little bit about the results in 3 degrees of freedom. So in analogy with the 2 degree of freedom problem, just remind you of the geometries in 2 dimensions. And then Thurston showed that there are 8 possible 3-dimensional geometries. I've separated these into 5 and 3. The 3 exceptional geometries on the right-hand column, these geometries here, are all associated in some way with hyperbolic geometry. Bolsanov and Taimanov's example is, as I said, a Sol geometry. Okay, and then of course we know the famous conjecture of Thurston, recently proven that conjectures that each compact 3 manifold is canonically decomposable into complete finite volume geometric 3 manifolds. So manifolds which are locally isometric to one of these 8. Okay, so to state the result in 3 degrees of freedom, which somehow encompasses Taimanov and Bolsanov's example, we need to introduce this definition, which is an attempt to define topological tameness. So, we suppose that the cotangent bundle is a union of 2 sets. Now, the large set L will be the bundle of regular Liouville tori. And this bundle in general is a non-trivial bundle. It's a non-trivial Tn bundle over some base manifold B. So for example, in the Bolsanov-Taimanov example, B is S1 times R2. So there's some topology in the base, which is one way of accounting for the interesting and exotic dynamical structures here. So we assume that the complement of our set of regular Lagrangian tori, gamma, is closed, nowhere dense, and here's the crucial thing, the thing that gives us topological control, that it's a tamely embedded polyhedron. So what I mean by a tamely embedded polyhedron is precisely that it has a thickening, it has a neighborhood, which is homeomorphic to a polyhedron, and it, gamma, sits inside as a subcomplex of this thickening. Okay, so this rules out wild sets like Alexander Horn spheres and other such pathological sets. Okay, and so this is what this setup here. I will call that a semi-simple integrable system. Taimanov, in proving his result that I quoted above, he introduced the notion of geometric simplicity, and this is a further generalization of this. He assumed that B was a disjoint union of disks, so that there were no topology in the base. So some examples of semi-simple Lagrangian fibrations. Any real analytic singular Lagrangian fibration fits into this. Why is that the case? Well, the singular set is a real analytic set, and it's an old theorem that a real analytic set is a tamely embedded polyhedron. Okay, a smooth singular Lagrangian fibration with a real analytic singular set. Well, the Bolsanov and Taimanov example gives us such an example. Okay, so there's the theorem then. Assume that so for simplicity, assume the geometrization conjecture. And then we know that a compact three-manifold admits such a semi-simple convex Hamiltonian if and only if it's geometrizable, and it admits one of those 5 geometries. And the backward arrow business is precisely by taking the geodesic flow of each one of the standard geometries on these manifolds and showing that they're completely integrable. So that's the easy bit, and the forward bit requires a little bit of work. Right. Okay. So moving on to higher dimensions, we know that in 2 and 3 dimensions that smooth structures and topological structures are the same. So in 56, of course, Milnor produced these examples of 7 spheres that are not diffeomorphic to the standard 7 sphere. And Milnor and Kerver, and independently Eels and Cooper, proved that there are exactly 28 smooth structures on the 7 sphere. And Milnor and Kerver actually showed that in all dimensions, the smooth structures on the n-dimensional sphere is a finite group. So in the 1970s, Walsh characterized the set of smooth structures on the topological n-dimensional torus, and he showed that this is essentially a group, although it is the group operation actually is quite mysterious. I don't believe that we understand that, but it is the direct sum of these cohomology groups with the coefficients sitting in groups of exotic spheres, at least for I not equal to 4. So one way of looking at this result is it tells us that there are lots of exotic smooth structures on the topological n-dimensional torus. Okay, so the lowest dimensional example where we have a non-standard smooth structure on the torus is in dimension 7, and we get 28 smooth structures by connect summing with exotic spheres. So just to sort of give you an appreciation, this was explained to me by Andrew Renitsky, how this wall result comes about. We can think about the problem of constructing exotic smooth structures in the following way. We've got the K-skeleton of our n-dimensional torus, and then we have to glue in a cell onto that K-skeleton. And what this result tells us is that if we take an exotic sphere and connect sum it with the standard cell that we've glued in, then this generates a non-diffeomorphic smooth structure. Okay, so this is a way also of seeing naturality of the smooth structure. So, and this is important for what I will state in a moment. By naturality, what I mean is that we have a manifold sigma, which is homeomorphic to the n-dimensional torus. And we can take finite coverings of the n-dimensional torus to itself. That will give us a finite covering of our topological n torus. Okay. And if we suppose that the smooth structure of sigma is characterized by this cohomology class little sigma lying in the sum of these cohomology groups, then the cohomology class of sigma prime, this covering, is exactly the pullback under the covering map of this smooth structure on sigma. So in particular, every topological n torus is finitely covered by a standard n torus, right? because these coefficient groups are all finite. Okay, so here's the theorem then. Suppose that sigma is a smooth n-dimensional topological torus, and then if the cotangent bundle admits a real analytically completely integrable convex Hamiltonian, then sigma is diffeomorphic to the standard n-dimensional torus. And I should note that real analyticity here is not absolutely essential. It's merely essential that we control the structure of the singular set and ensure that the base of our singular Lagrangian fibration is not too highly connected. So we can relax this to semi-simplicity plus the assumption that the base is got a finite fundamental group. Okay, so in particular, the existence of an completely integrable convex Hamiltonian with this additional topological tameness singles out the smooth structure on the configuration space. Okay, so I'd just like to run through it because it's a relatively straightforward argument. All of the work is really done by an old result of Viterbo's. So what we'll do is show, or at least indicate, that we can find a Lagrangian torus inside the cotangent bundle of our exotic torus. Now, when we restrict the fiber projection map to this Lagrangian torus, what we want to do is deduce that the degree of this map is non-zero, and then we'll pull this picture back to a finite covering where we have the standard smooth structure on the base sigma prime, and then we'll use an argument, a result of Viterbo's, that says that when the degree of this projection map is non-zero, that implies that rho is a covering map, and then we'll use a simple argument to show that it's actually one-to-one. Okay, so the first part of this result, the heavy lifting, is provided by a lemma of Taimanov's, and it tells us that there is such a Lagrangian torus inside of our set L, where the map on fundamental groups is almost surjective. So we have a non-zero degree map. And then, as I said, and then we use this result of Wall and the naturality of the smooth structures with respect to covering maps to pull this picture back to this finite covering where we have a standard smooth torus and its cotangent bundle. Okay, so just to see how this result runs, how Viterbo's argument runs, we have our Lagrangian torus sitting inside the cotangent bundle of the standard n-dimensional torus, and we want to show that this map rho prime, that it is a local covering map. of course, the instrument needed is the Maslov cycle, which Ellie Kerman talked about yesterday. So here, this is a winding number. So the top picture here gives us a Lagrangian torus in the cotangent bundle of the one torus with Maslov class 2. And then there are these two Lagrangian tori here, which both have 0 Maslov class. But in the second case here, we've got this business where the projection map onto the base S1 is not a covering map. So we use convexity to rule out this sort of badness. All right, so as I said, Viterbo proved in 91 that if we have this standard n-dimensional torus and a Lagrangian torus inside its cotangent bundle, and we have this, the restriction of the projection map has non-zero degree, then necessarily the Maslov class of F vanishes, and that means that we're in the situation where potentially F has where potentially the singular set of this of this projection map rho prime is has some singularities, but they're null homologous. But then Bialy and Polterovich have this nice little argument which says that if F prime is convex, right? So in other words, if it's lying in the isoenergy set of a convex Hamiltonian, then that forces rho prime actually to be a covering map. Okay, so that tells us then that the Lagrangian torus F inside the cotangent bundle of our exotic torus, that this is a smooth covering map. But that actually hasn't told us very much, right? It's gone some distance to what we want to prove, but it's still possible that that this is a non-trivial covering map. So we want to show that it's one-to-one, right? We want to rule out the possibility that the Lagrangian torus F looks like the green part of this picture. We want to show that this looks like the blue part. So here's a little argument that explains why this is the case. We know that both F and sigma are topological tori. So we decompose the Liouville-1 form into a bit which is invariant under the action of the deck transformation group of our covering, plus some residual bit that's exact. And then we just look at the action of some element in our covering group, and we look at the difference of the pullback of our Liouville-1 form under this deck transformation. And we see that the difference is exact. And on the other hand, we unravel the definition of the Liouville-1 form, and we see that it's the difference of these two one forms, right, sitting in the cotangent space to sigma at x, pulled back by our projection map. But of course, this part here has to vanish somewhere, and so since we proved that the map rho is a local diffeomorphism, that forces x minus gamma to vanish somewhere, and that forces gamma to have a fixed point, and hence it's the identity map. And so that forces our entire deck transformation group to be trivial. So this gives us a diffeomorphism, right? Rho is a diffeomorphism from the standard n-dimensional torus, this Lagrangian torus, to the base sigma. And so that gives us a smooth obstruction to the existence of a convex Hamiltonian. And now what I would like to do is to show that this invariant is non-trivial. So unfortunately, I don't have a theory why it's non-trivial. I can't characterize the invariant. All I can do is say, well, here's an example where all the smooth structures do have completely integrable convex Hamiltonians. and leave it to someone smarter than me to figure out how to characterize this smooth invariant. Okay, so in the early 80s, Witten proposed a model for supersymmetry in 7 dimensions using these homogeneous spaces of U3 times U2 times U1. And here we'll use a result of Kreck and Stoltz from the late 80s, which characterized the smooth structures on these spaces. They're more easily, for my purposes, viewed as bases of S1 fibrations with total space S3 times S5. Okay, so Kreck and Stoltz characterized the smooth structures on all these spaces, and I'll just give you one where they showed that all smooth structures are of this form. So M14 admits 28 smooth structures. And the difficulty from my point of view is that I want all the smooth structures to have representatives that are represented by Witten-Kreck-Stoltz spaces, so that can be represented as bases of these S1 fibrations. And M14 exactly fits this bill. Okay, but on the other hand, if we look at this manifold MKL, it is fairly apparent that if we take the product of round metrics on S3 times S5, that is certainly going to be invariant under the action of this group U, right? And then it's just a matter of writing down or quoting the appropriate result, which tells us that the reduced flow is completely integrable, and that's the case. So result of Parasuk and his collaborator tells us that this is true in general. On the other hand, there, yeah.
So what do the integrals come from in that example?
Right. So the easiest way of thinking about these integrals, they come about from the translation of arguments, or lax representation. So you write down concretely a lax representation for the product of round metrics on these two spheres, right? And then you choose the lax representation in such a way that it respects this, it commutes with this action here of U. So it's not an explicit. What am I saying? The formulae are not exactly explicit, although I can in my paper I do write down the result. Do write down the integrals in some examples. Okay, but so basically the difficulty is ensuring this U invariance, right? Yeah. So the argument follows. Actually, the argument is in your paper with Spazier. Right. All you have to do is show that restrict. So you look at. Inside of the full cotangent bundle of the total space, you've got the zero momentum level for this group U, right? You have the integrals which you've ensured are S1 are U invariant, and then you simply choose a point suitably chosen inside this set here where all the integrals are independent, and since they're analytic integrals, they're independent almost everywhere. Yeah. Okay. Now here's another. So if I can just back up a little bit, what we've seen so far is that in the topological n-dimensional torus, we have a dictatorial situation. We have exactly one smooth structure is singled out. And in the Witten-Kruggel spaces, we've got the completely egalitarian situation where all 28 smooth structures are equal from our point of view. And what I would like to do, what I was hoping to do, but have not been successful at doing, is to find examples of somewhere in between to see that this invariant is truly non-trivial. So here's a potential class of spaces where we may have the situation being somewhere between dictatorship and democracy. So the Eschenburg in the early 1980s introduced these spaces, some of which admit positively curved Riemannian metrics, and these spaces are not homotopy equivalent to a homogeneous space, so they were interesting from the point of view of Riemannian geometry for that reason. Now, Kruggel, in his PhD dissertation, which was done in the 90s but only published recently, characterized the smooth structures on some of these spaces. So these are biquotients of SU3 by the action of these the product of diagonal subgroups. Okay. Kruggel, to classify the smooth structures, introduced this condition C, and we form this matrix of the difference of exponents on the left and the right subgroups, and then we say that condition C is satisfied if this matrix has at least one column or row with pairwise coprime non-zero entries. Okay, so why this is important for Kruggel's point of view, we have our Eschenburg space EKL, and we have an S1 vibration over this space. Now, SU3 is the same as the Stifel manifold of complex two planes in C3, and the action here extends to what I will call W hat, which is a bounding 8 manifold. So the business of smooth structures on 7-dimensional manifolds always amounts to the business of finding a bounding 8 manifold and calculating invariance of this bounding 8 manifold. So this is let me get the dimensions correct. So this is 9 dimensions, and then we reduce to not a manifold but something else. Okay, so we fill in we fill this manifold in so that it bounds a 9-dimensional manifold, and the action of U extends to this 9 manifold. The reduction gives us an 8 no, it doesn't give us an 8 manifold. There are singularities. So what we do is we cut out. There are 3 singular points. We cut out the an equivariant neighborhood of each of these 3 singular points. And the neighborhoods are lens spaces. So the boundaries of those neighborhoods are lens spaces, right? And so there we've got an 8 manifold here, W, whose boundary is the disjoint union of our Eschenburg space and 3 lens spaces. And this obtains, this decomposition of the boundary obtains if we have this condition C satisfied. It's a horrible name for the condition, but it guarantees that the Eales-Cooper invariance can be calculated by calculating the invariance of the bounding lens spaces. So Kruggel, using the Kruggel-Stolz invariance for 7 manifolds, deduced the following, that these spaces are homeomorphic if H4, which is a finite group, if their ranks are equal. It's a finite cyclic group. Okay, so the ranks have to be equal. The linking form on H4 has to be isometric, and the Pontryagin eigenclasses must be equal. And the second step, Kruggel-Stolz, has to be equal. Okay, and then they are orientation preserving diffeomorphic if, in addition, the first Kruggel-Stolz is equal. And the thing that makes this problem much more difficult, so essentially the same thing is true for the Witten-Kruggel-Stolz spaces, but there the Kruggel-Stolz invariance can be expressed as polynomials, and so it's very easy to write down conditions for equality. But here, the bounding lens spaces, their Kruggel-Stolz invariants are transcendental functions. So we have some difficulties in showing that these spaces are actually homeomorphic or diffeomorphic. All right, so here's a theorem. Paternain and Spazier proved for a particular Eschenburg space that the geodesic flow coming from the bi-invariant metric on SU3, that geodesic flow is completely integrable with analytic integrals. And Bazaikin extended this to all positively curved Eschenburg spaces. He did this using a different representation, and it's not so immediately obvious that all of the spaces do admit integrable convex Hamiltonians, but the symmetry picture continues to prevail. So with the right lax representation, you can show that the bi-invariant metric on SU3 induces a completely integrable convex Hamiltonian on every one of these Eschenburg spaces. Okay, and so finally, this is kind of a negative result because, as I said, I wanted to find examples where we had a situation in between dictatorship and egalitarianism. Here is a search for the smooth structures on the first example given by Paternain and Spazier. And here we see that actually all the 28 smooth structures are represented by, again, Eschenburg-Kruggel spaces, so they all admit completely integrable convex Hamiltonians. So we don't really have any additional information about this smooth invariant. However, here this example is in the simplest case where the rank of H4 is sorry, not the rank, the order of H4 is equal to 1. So doing some calculations, I've been able to show that all of the Eschenburg-Kruggel spaces with the order of H4 being 1, all of those spaces topologically, every smooth representative is represented again by an Eschenburg-Kruggel space. So there's no hope there, but possibly in higher rank, there is a potential for finding some examples. Okay, so finally, let me finish on the following notes. So really, we have, in addition, these results, these non-existent results, are also open questions, right? So the most basic question is the existence of an integrable convex Hamiltonian on the cotangent bundle of a higher genus surface. We know that the singular set of such a system would have to be wild, but there's no reason to believe that such a system could not exist. At least that's beyond our technology at the moment. And the same is equally true for completely integrable convex Hamiltonians on exotic tori. this result is suggestive. Possibly there are no such things. Another question would be, we know in genus 2 or more that the geodesic flows must have positive entropy and complicated dynamics. Is a similar theorem true for these exotic tori? Does the smooth structure necessitate the existence of complex dynamics in the geodesic flows or convex Hamiltonian flows? Can someone is there a good description of this smooth invariant other than to say that it's non-trivial? And finally, this is a more broad question. Must the entropy of an analytically integrable system in degree of freedom 3 or more have 0 entropy? So that's a question which follows on from the result of Patterning and Moser's that I quoted at the outset. So I thank you for your attention.
Are there more questions?
It's not. You mean the result of Bazaikin, who proved for positively curved Eschenburg spaces?
Yeah. So there's lots of like almost examples.
Yes. No, what Bazaikin did was he showed that there is an alternative representation of these spaces as bihomogeneous spaces, and from that he constructed integrals. But the point is that you actually don't need that alternative representation of your Eschenburg space in order to get your integrals. You can do just write down the right lax representation and everything follows naturally.
More questions? Comments? So let's thank Butler again.